Okay, welcome. We're going to take a look at the first half of section 5 today. And there's a lot of information here, and hopefully we can get through this and make some sense out of it. But we start with a one-to-one function, which if you have background with one-to-one functions, one of the most important things to know about one-to-one functions is that it is almost synonymous. If a function is one-to-one, then it has an inverse function. And if a function has an inverse function, then it's one-to-one. So this is one of those geometry if and only ifs. A function is one-to-one if and only if it has an inverse function. That's a very strong correlation. It's almost like a definition. They go hand in hand. So a function f of x is one-to-one on a domain D, some chosen values of x. If f of a chosen value of x is not equal to an f of the height at A, some chosen value of x is different than the height of B whenever A is different than B. Here's what that means, and this is going to make more sense just outside of the realm of math. I say a one-to-one function is kind of like if we had a graph, kind of silly example, and we said that, let's say the x-axis is our girls in school that might be interested in going to homecoming, and this is boys in school. So for instance, if I had a point over here at 1, 2, that means that girl 1 is going to go to homecoming with boy 2. Now we know mathematically that this guy right here is a function. It passes the vertical line test. But in terms of our homecoming dates, this means that, let's say this is up at negative, or let's say this is up at 1. This means that boy -1 is going to homecoming with girl 1, and boy 2 is going to homecoming with girl 2, and boy 3, 4, 5 is going with girl 1. Boy 2 is going with girl 1. It's not a one-to-one situation here. So the easiest way to determine if a function is one-to-one is to look at the graph, picture the graph, and realize and ask yourself, does it pass the horizontal line test? That's a one-to-one function. Therefore, here's a one-to-one function right here. That's a one-to-one function. Passes vertical line test, so it's a function. Passes horizontal line tests, it's one-to-one. Okay, so that's one-to-one function, but again, remember the important part of it is that's when a function has an inverse, is if it's one-to-one and vice versa. Okay, writing f inverse, the inverse function, as a function of x. Solve the equation y equals x for x in terms of y. Interchange x and y. All right, this is going to make a lot of sense when we realize an inverse function, the most base thing to know about an inverse function is it turns x's into y's and y's into x's. In other words, if I have a function, simple little function, let's say my function, the only thing about it is that -1, 3. That's my whole function right here. If -1, 3 is on my function, then on my inverse, I should have 3, -1. At the very most base level, an inverse function just takes x's and turns them into y's and y's and turns them into x's. As it so happens, that results in a reflection over the line y equals x. Okay, so we'll come back to that and make some sense out of that. All right, base A logarithm, base A log function. I would like all of you to realize and be able to recite that this is the function that turns A into x. Worth writing this down. I'm not going to write it here, but worth writing this down. A logarithm is the function, a logarithm is the exponent that turns its base, in this case A, into its argument, in this case x. Now, saying it and understanding it are two different things, so we're going to hit that a little bit here as we move on. So if this whole thing is the exponent that would turn A into x, and this thing is equal to y, then y is the exponent that would turn A into x. And then it says the inverse of that is this. Look what they've done. What was y becomes x. What was x becomes y. Yep, those things are inverses. Okay. Properties of logarithms. Let's go through this in the words again. We would say this is the exponent that turns a into 1. Well, a to the what equals 1? Anything to the first, any non-zero value to the 0th equals 1. So this is 0. What is the exponent that turns a into 1? 0. What is the exponent that turns a into a? 1 is. Of course, a to the first is a. Now this one's a little bit tricky for people at times. This little log ax. Log base a of x. Got to follow this one closely. This is the exponent that turns a into x. So log ax is the exponent that would turn a into x. Well, it has met its calling. The exponent that turns a into x is log ax. So log base a of x, this is like it's destiny. I wanted to be an exponent. I want to be an exponent on a and make it become x. Well, I'm an exponent on a, so I make it become x. Kind of weird. I often say this would be like finding a really sharp 5th grade math student and say, hey, I want you to work this out. I want you to take 15 times 27 and divide 15. And that student's not going to have to spend too much time on that problem, as you wouldn't either. So a really good calculus student, pre-calculus student that really gets logarithms is going to see this one right away. Oh, are you kidding me? Why would you waste my time with that? Likewise, this whole thing is the exponent that would turn a into a to the x. So I need an exponent that would turn a into a to the x. Well, of course, it's just x. What is the exponent that turns a into a to the x? X. Okay, then we have these properties. I'm not going to go into the whole explanation of why, but this first product rule has an awful lot to do with why we know that x to the second times x to the third is x to the fifth. Notice we end up adding exponents. Well, this is an exponent, this is an exponent. Notice we have a product. Here's a product. We have common base of x. Here's common base of a. We add the exponents. Quotient rule has a lot to do with why x to the fifth on x to the second is x to the third. We subtract exponents. When do we subtract them? When we have a quotient, exponents, common base, common base. And this last one has a whole lot to do with x to the second to the third being x to the sixth, which we're all comfortable with. What's going on here? I have an exponent y with an exponent. Well, log ax is an exponent, so I have an exponent and an exponent. An exponent and an exponent. We multiply the exponents. Y is an exponent, and log base a of x is the exponent. 2 times 3, 6. Change of base formula. I believe we're all familiar with change of base formula. Here's a quick example. If I have log base 7 of 13, I can rewrite that as log base 13 on log base 10. I could rewrite it as ln 13 on ln 10. I could rewrite it as log base 2.1 of 13 on, this should be 7, I'm sorry. I was thinking log base 10, this should be 7. Is log 0.21 on log base 2.1 of 7. My apologies on that. But we can basically choose any log we want. This is going to, if I'm using this, I'm very typically going to go to ln's. That's just my habit. Most people typically go to ln's or to plain old log. Okay. All right, let's look at some examples of these things. Now, we could go to graphing calculator on every one of these and look for horizontal line tests. Because remember, we said it on the previous page, if a function has an inverse function, it will pass the horizontal line test. But I would like to think that maybe we know what the graph of y equals, let's say 1 on x looks like. Graph of 1 on x. And even if we didn't, quick t-chart. Put in 1, get out 1. Put in 2, get out a half, a third, a fourth. getting sucked into this asymptote. Put in a half, get out 2, put in a third, get out 3, 4, 5. X can't be 0. Put in -1, get out -1. In fact, this is an odd function because if I put in the opposite value, if I put in -x, I get the opposite of 1 on x. So it's symmetric about the origin. Now this function is 1-to-1. How does this function relate? It would be 2 to the right. Moving this 2 to the right, still 1-to-1. 3 times as tall. Well, 3 times as tall would just make it where it was 1, it's 3, but 0 would still be 0, still an asymptote. And move it down 1. Yeah, this thing is still going to be 1-to-1. It will pass horizontal line test. B. So this is, yes, it has an inverse function. We're not finding it now. B. The graph of this, hopefully what we know about this is it has a y-intercept of 6, and as it goes through there, the next thing it wants to do is look like the line -4x for an instant. The last thing it wants to do is look like a positive cubic, so this is eventually going to come back down. This is eventually going to go back up. Now maybe it goes further, but what I know for sure is, because these oppose each other, one's going down, the other one wants to go up, this thing does not pass horizontal line test. So no. All right, C. Even if I didn't know what the graph of this looks like, real quickly, when I see that squared on x, ln of 2 squared is going to equal ln of -2 squared. Therefore, from my example on the page before, girls for the x-axis, boys for the y-axis, girl 2 and girl -2 would end up with the same date for boy. They're going to end up both being ln 4. So it's not 1-to-1. This graph, and it's most very basic. This is it's a parabola. Next, we know it opens upward. This is a parabola. I don't even care where it's located right now. It's not going to pass horizontal line test. No, no. This graph is a cubic, and you may say, well, cubic, we had a cubic before, and it was a no, so this one must be no. Well, this one passes through 0. It's going up pretty steep, and then it wants to go even further up in each direction. This thing's just going to look like that. Yes, passes horizontal line test. Okay, I'm going to rewrite this as y equals 3 to the -x plus 2. Maybe we know what y equals. Let's just work with y equals 3 to the x. You could do this on your graphing calculator. I put in 0, I get 1. I put in 1, I get 3. I put in 2, I'm all the way up to 9. I put in -1, I get a third, a ninth, 1/127th, looks like this. This is just a transformation of that. Most interesting value of x is 2. It makes my exponent 0, so that's 2 to the right. And then backwards. Or backwards, then 2 to the right. Anyway, this is just a transformation of this. If this thing's transformed, it's still, wherever we move it around to, is going to pass the horizontal line test, so this is a yes. Okay, find F inverse. F inverse, what did we say is the most basic thing we need to know about inverse functions? And that is we change y into x, and we change x into y. And then all we need to do is solve that for y. So y equals, let's see what we get here. I started with x. I would subtract 3. I would divide by 2. There's solve for y. Therefore, F inverse of x is x minus 3 on 2. And then we're to show that f of f inverse of x equals x. So that is f of f inverse. F inverse is x minus 3 on 2. That equals, well, f is a factory that takes things and puts them right there. No matter how ugly the thing is, it's going to put it right here. And I get 2 times x minus 3 on 2. I put the thing right there, and I still have to add 3. 2's cancel, x minus 3 plus 3 gives me x. And then we're supposed to show that f inverse of f is 2x plus 3, equals x. And I will leave that to the reader. It's the same process again. Okay, B, same thing. Inverse functions, y's become x's, x's become y's. We solve for y. We started with an x. We add 1. Then we would take the third root. So f of f inverse, this is f inverse of x now, f of third root of x plus 1. F is a factory that takes things no matter what they look like. Now it looks like this, puts it right here. Third root of x plus 1, then we cube it, then we subtract 1. Gives me x plus 1, cube cancels cube root, minus 1 equals x. And again, at that point, f inverse of f of x, but it's pretty much the same process. Okay, kind of an interesting one here. My eyes are kind of drawn to this x is greater than 0, so I'm going to take a look at the picture here. If I put 0 in, oh, I can't put 0 in, so we know we have an asymptote, or perhaps have an asymptote, maybe a hole in the graph, but let's take a look. If I put 1 in, I get 1. If I put 2 in, I get a 4th, 3 in, a 9th, a 16th. Clearly we're getting pulled into the x-axis. If I put a half in, I get 1 on 1/4, which is 4. If I put a third in, I get 9. So we look like this. Now, if I was allowed to let x be less than 0, when I put -1 in, I quickly discover, hey, this is an even function. 1 on -1. If I put negative x in here, the negative gets absorbed when we square, so this side would look like this. We're going to come back and talk about that in a bit. So x's become y's, y's become x's, we solve for y. If I cross multiply, I get y squared x equals 1, y squared equals 1 on x, and y equals plus or minus the square root of 1 on x, or square root of 1 is 1 on square root of x. And you could call that plus or minus rationalized, multiply by root x on root x, and we get that. Could call it that. I'm going to probably work with this one. Now, as soon as I see that plus or minus, I immediately know we're either not working with a function or we're not working with an inverse function. And remember, inverse functions are symmetric across the line y equals x. And we're only dealing with this right side. So my symmetry across here would take this point to here, and 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 this point right there. My symmetry would stay virtually, maybe exactly the same curve. We could study that, but it would definitely stay in the first quadrant where our y values are positive. So I'm going to reject the negative option here and just use 1 on square root of x. Okay, so f of f inverse, I'm going to use this version of it, is supposed to equal x. Let's see. F is a factory that takes things, even if they're a mess, and puts them right there. 1 on the mess, 1 on root x, but then we square it. And that becomes 1 on 1 squared 1, square root of x squared x, which is equivalent to, of course, 1 times x on 1, or just x. And again, I'm going to leave the second half of that to the viewer. Okay, D. Algebra gets a little bit messier here. I'm not exactly sure what the graph of this looks like, but I'm just going to go ahead and start the process. What do inverse functions do? They turn y into x, and they turn x into y. We solve for y. We'll have awfully good algebra students. Sometimes can't do this or get stuck. I'm going to cross multiply because I don't like y's in the denominator. xy plus 3x equals 2y plus 1. And then I need to group my y's on the same side. I get xy minus 2y equals, I'm going to subtract 3x, joins the plus 1. And I'll see good students get stuck here. What's offensive about this now? I don't want two y's, I just want a y. I can get a y by factoring out. Divide x minus 2 and I get negative 3x plus 1 on x minus 2. Now, I need to point out, so this is f inverse. I need to point this one out. You might do this problem, it might be an odd, it might be in the back of the book, and the back of the book might say 3x minus 1 on 2 minus x is what we should have. Oftentimes on fractions, they're going to try to maybe not have a negative as the lead term if it's a rational in the numerator. So you need to be aware, yeah, we can multiply by negative 1 on negative 1, and we would clearly get this. I'm going to go ahead and use this guy. We're going to need some space for this. So I need to show that f of my inverse function, negative 3x plus 1 on x minus 2, is equal to x. Well, f is a factory. It's going to be a mess that puts things here and here, and it doesn't. How? So what I've got is a mess going into something that creates a mess. I'm going to get a messy mess here. So this is going to take the place of that x. This whole thing is going to take the place of that x, and I get 2 times negative 3x plus 1 on x minus 2 plus the 1 equals negative 3x plus 1 on x minus 2 plus the 3. We most certainly may not cancel these. This negative 3x plus 1 on x minus 2 is not a factor of the numerator or the denominator. We cannot cancel them. I would multiply top and bottom of this by my least common denominator out of this term, this term, this term, and this term. When I multiply this, I'm going to distribute the whole x minus 2 to this whole first term. The x minus 2's cancel, and I get 2 times negative 3x plus 1. I still have to distribute x minus 2 to the 1. I get plus 1 times x minus 2. In the denominator, x minus 2 to this first term, the x minus 2's cancel, and I get negative 3x plus 1. Plus x minus 2 times 3, 3 times x minus 2. Let's see, what do I get in the numerator? X's. Negative 6x plus an x, negative 5x's. I get a 2 plus a negative 2, cancel. In the denominator, negative 3x plus 3x, cancel, and 1 plus negative 6, or 1 minus 6, negative 5, and I get x. Again, probably a really good idea to practice this the other way around, where we find f inverse of f. And finally, we got some functions here. This can be maybe a little, we'll see how this is on this projector. I'm going to want to use parametric graphing to graph y equals e of x, and the inverse of this, and y equals x. And the best part about this is I don't have to find the inverse functions if I use parametric graphing. So I'm going to do some zooming in here, and we're going to remember that this function is e to the x, because I'm going to have to change my light settings on this. So let's go ahead and turn this on, because you see we'd have a big mess if I didn't do that. So I'm going to go into my y equals. As I zoom, I want to clear a few things out here and get ready to talk about these. I'm going to get this to a point where we can see it. So let's go zoom. Let's get in on this guy. And let's see how we can do here. If I turn my brightness down, there we go. Okay, now remember the first function that we were looking at was e to the x. So parametrically, I had y equals e to the x. So parametrics obviously introduces this value of t. I'm going to just let x equal t, and that's going to kind of be my theme. And then I'm going to let y be my function. My function was e to the x. So second, e to the x, but that's actually t now. Now, this is clever but simple if we remember. If we just knew that inverse functions, all they do is change x's to y's and y's to x's, and this second function is going to be my inverse function, then I want what was my y to be my x, and my y was e to the t. So my x is e to the t. My y becomes what my x was t. And then the third line that they talk about, and I don't think you'll see this well. Oh yeah, you do. The third thing they talked about is they wanted also the line y equals x. Well, if I let both of these be t at the same time for my third curve, isn't y equal to x if they're both equal to t? Okay, my recommendation on this for this lesson is in Windows, we let t min be negative 10 to 10, my t values. I let my x's be negative 10, and you could have to search around sometime if you don't do this. My y min to be negative 10 to 10. And as I graph this, my first function was e to the x. That was the blue one. My second function is the inverse. And my third function is just y equals x. And as we can see, it appears like maybe there is symmetry across there, which we talked about. So that easy. Okay, let's take a look at this next function, y equals 2 to the negative x. Watch how easy this is. All I need to change is make this 2 to the negative t. So if y's become x's and x becomes y's, then this should be, my x value should be my other y value for inverse function. 2 to the, not negative 2, negative t. And I just want y equal to x. Graph this one. First function, second function, my mirror function, y equals x. Yep, it looks like if I flip the blue graph over, maybe it would lie on the red graph. Notice they all three intersect in a point. And the last one here, the last function here, sine inverse of x. So back into y equals, clear, second sine inverse of t, which is my x value, which means this one should be sine inverse. If I was just graphing this parametrically, or not parametrically, but on Cartesian, then I'd graph one as sine inverse and the other as sine. Those are inverse functions. But I'm changing x and y, so I'm just going to call this second sine inverse t. Now, for this one, I don't think I need that parenthesis, but I'm going to put it there. For this one, when we graph it, take a close look. I get a tiny little squiggly there for blue, a tiny little squiggly for red, and now I'm going to, the perfect time to zoom box. I'm going to zoom in on this, and that is just to build a little TV screen around the interesting parts. So all my interesting part lies between here, and I'm building a rectangular box around there. And now once I'm past everything, I'm going to stamp enter. This blue graph, I'm tracing it down. Starts down low, goes up high. It looks sort of like a cubic. That was the inverse function. This red graph, that's part of sine. The inverse of sine inverse is sine. It could look familiar, and it does look like we're symmetric. So if I come back to this just for a minute and talk about sine, we know the graph of sine looks like this. So what about its inverse function? Well, it doesn't have an inverse function. It doesn't pass the horizontal line test. So we have to lop that off from negative pi on 2 to pi on 2 to have this portion of the graph. That is 1 to 1, and that's what we see right here in that red graph, that graph that goes across here, that is that little chunk of sine that is allowed to have a sine inverse. How smart are our calculators? And that leaves you with some assignment to do. We have more to talk about on Chapter 5. We'll be taking a look at that tomorrow. Thanks for stopping in.